This is lesson 8 in the Forces and Balance topic entitled Moments at Work. Please note that this is purely for triple award students only. During the course of the lesson you should be able to define what we meant by the term moment of force, recall the factors affecting the size of the force, be able to calculate the moment of a force, and be able to apply the principle of moments and use it to determine whether objects will balance. Okay, before we get going, take a look at this situation which occurred a few years ago back in Ireland. A car had ended up in the harbour here and they were trying to recover it from the harbour. All's going well. Oh dear. What we need is a bigger crane. Success. Nearly. Okay, so sometimes a bit of physics knowledge will help you out in nasty situations. So, moment of a force, what is it then? You'll need to put that title in your notes and pause the video when I finish talking to get this note down. So, what is the moment of a force? It is the turning effect of a force. Okay, its ability to turn, it's a measure of the ability for a force to rotate or turn something. The bigger the moment, the greater the turning effect, and it can be calculated using the equation moment equals force times perpendicular distance from the pivot. If we look at that on the diagram there, so the moment would be the size of the force multiplied by this distance here, the perpendicular distance from the pivot. Now force of course must always be measured in newtons, but sometimes we have the option with distance. Here it's measured in meters and our moment would be measured in Newton meters. If that were in centimeters, then our moment would be in Newton centimeters. Pause the video and make sure you've got that as a note. Okay, let's look at a specific example now. Again, this is for your notes, so you need to pause it at the end to make sure that you've got your calculation done. Okay, so Gina weighs 500 newtons and stands on the end of a seesaw. She's 0.5 meters from the pivot. What moment does she exert? So just give you a few moments to copy that down and then have a go at the calculation. What is her moment? Okay, pretty straightforward this then. Her moment is simply her force, her weight, 500 newtons, multiplied by the distance she is from the pivot here, 0.5 meters, which gives 250 newton meters. Okay, so how does all this relate to not tipping over a crane into the ocean? Well, in order to prevent incidents like that happening, you have to recall something called the law, or often called the principle of moments. And the law or principle of moments simply says that for an object to be in equilibrium, balanced, the anti-clockwise moments must equal the clockwise moments. So if we take a moment just to look at the situation here, we've got a seesaw which is balanced on the pivot here. We've got two weights exerting a force F1 in that direction, a distance D1 from the pivot, and here you've got a single weight with a force of F2, a distance D2 from the pivot. And all we're saying is for that seesaw to balance, the force times the distance from the pivot on this side must equal the force times the distance from the pivot on that side. Pause the video and make sure you've got that note in your books, please. Okay, it sounds complicated, but it's not. So let's look at some examples. You might like to pause the video, see whether or not you can work these out before I give you the solutions. Okay, so let's have a look at some. Okay, so the question is balanced or unbalanced. The top seesaw here, we've got a single weight which is 1, 2, 3, 4 units away from the pivot, and on the other side we've got no weight at all. Well, I think even without a physics lesson you'll be able to work out what happens there, but mathematically what is happening? So the law of moments says that the anti-clockwise must equal the clockwise moments if that seesaw is to balance. Well, we use these little symbols here to represent anti-clockwise here, and this will create an anti-clockwise moment. It'll make this end of the seesaw tip downwards, that to go up, so it'd rotate like that in anti-clockwise fashion. So the anti-clockwise moment here would be one weight, 1 newton if you like, multiplied by 4 units of distance, could be meters, could be centimeters. 1 times 4 multiplied by is equal to, or in this case not equal to, no weight on this side, therefore no distance. So that seesaw will tip anti-clockwise. This one's a little bit tricky to think about because we've actually got a weight on this side now. The question is, will that seesaw balance? Just pause the video and see if you can work it out. Okay, so on the left hand side, this is going to create an anti-clockwise moment. The force is 2. It is 2 units away from the pivot, so 2 times 2 is 4. This is 1 away from the pivot. Sorry, this is a 1 Newton weight. It's 4 units away from the pivot, so its moment is 1 times 4, so it'll balance. Now this one here is slightly trickier because you've got 2 weights on the left hand side but not in the same position. So to deal with this, you work out the moment of this weight here and the moment of this weight here, and then you add the moments together. And once again, if the moments on this side, the anti-clockwise moments, is equal to the clockwise moment on this side, it will balance. So see if you can work that out now. Pause the video. Okay, so on this side then we've got 1 weight times a distance of 4 plus 1 weight at a distance of 1. There's our calculation there. And if it's to balance, that must equal 2 weights at a distance 2. Well, you can see quite clearly here that's 4 plus 1 is 5. That is not equal to 2 times 2, so it won't balance. And because the moment is bigger on this side here, it'll again tip anti-clockwise. And finally, the last one, have a look at that. A little bit more complicated this time, because you've got weights 2 different distances on both sides. But you should come up to the conclusion that the seesaw will balance. And that should be a little equal sign there, not a not equals to. So 1 times 4 is 4, plus 3 is 7, 2 times 2 is 4, plus 1 times 3 is 7. It will balance. Okay, to make sure you've got to grips with that, I'd like you to now visit the PHET site, P-H-E-T, University of Colorado. If you type into Google PHET, chances are it'll come up with that, but there's the web address if you need it. The simulation we're looking for is a balancing act. Okay, you can see that there. If you click on there, it'll download to your computer. Have a look at the intros, and then have a go at the game, see how well you can do at balancing those seesaws. You'll notice that they haven't given weights, forces in newtons, they just simply use kilograms, but just think of them as being newton weights. Okay, very quickly then, to review, you should know that the moment of a force is a measure of its turning effect. You should know that the size of the moment depends upon the size of the force applied and its distance away from the pivot. You should be able to calculate moment using moment equals force times perpendicular distance from the pivot, and recall the principle of moments that states that a body will be in equilibrium or balanced if the sum of the clockwise moments is equal to the sum of the anti-clockwise moments, and be able to apply that to different situations.